Hi, so my name is Thomas Humbert, and I'm working at l'Homme in Le Mans with Yves Aurégan and Joachim Golliard. And today I'm going to present some new results we have on corrugated tubes. So corrugated tubes are tubes with periodic change of the inner diameter. And you have surely already met them, for example, in vacuum cleaner, or with people making some sound by spinning them in the air, or also in industrial application like offshore platform. And so we are interested in these tubes actually because beautiful physics is happening inside of them because of the cavity. And so when the flow is inside the tube, depending on the size of the cavity, you will have, so in all cases, you have a shear layer, and sometimes it can lead to vortex generation. But as in our case with small cavity, you just have, as it can be seen on these LDV measurements of the velocity, some stable but shear layer above the cavity. And so in fact, sometimes depending on the flow velocity, you can have a coupling between the acoustic and the flow. And for example, in the industrial case of offshore platform, it can lead to strong whistling and sometimes to accidents and breaking of the tubes or the surrounding environment. And so we are interested in understanding how this whistling is produced. And it's been some years that people at LOM and in other labs are working on that subject. For example, last year we published this paper when we were measuring the scattering matrix of the same corrugated tube that we use today. And what we have shown in this paper that depending on the flow velocity, as it can be seen on this, on the left, the transmission coefficient, there are some frequencies where you have additional damping because of the flow sound interaction in the tube compared to the no flow case in brown. And for higher frequencies, you have amplification of the acoustics because of the sound flow interactions. And this those range of frequency with additional losses and gain will be determined by the flow velocity. And the faster the flow, the higher will be this amplification zone. And this in resonant condition can lead to whistling. But today, I want to use another point of view and stop talking about propagating waves, but duct modes and cavity modes in presence of a gain medium, which will be my corrugated tubes. So this has been inspired by physics of lasers. When you have a cavity with some electrons and with electrical excitation and a gain medium, you can have a stimulation of production of photons and emission of one color, one wavelength coherent emission of light. And so we want to do quite the same thing, but with acoustics and flow. So we just put corrugated tubes between two cavities, so resonators with a large diameter compared to the tube. There are some acoustic sources to provide acoustic waves upstream the corrugated tubes, and everything is also plugged to a fan that will provide the flow. And we have microphone inside the cavity to measure the propagating waves or the acoustics, let's say, inside the cavity. And so with the measurements and even two microphones, since we have only plane waves in this experiment, we can define a reflection coefficient that will lead to the definition of an impedance. So actually here I'm displaying the impedance without flow. So we can see some peaks that actually corresponds to the modes of this cavity formed by the two resonators. And so the distance between each peak corresponds actually, there is a simple relation with the distance between the two cavities. But what is interesting here is that when I add some flow, I will see that the mode shape is changing. So if you take the slow flow, m0.016, where m is the Mach number, flow velocity over sound velocity. If you look at the low frequency modes, you will see that the peaks are much narrow, or let's say narrow, as compared to the no flow case. Whereas for the faster flow 0.025 Mach number, you can see around 800 Hertz some very, very narrow peaks. And so actually this means that with the flow, we can control the damping of each mode in the duct, because you remember that the width of an impedance peak is directly linked to its inner damping. When we, with the flow, introduce very narrow peaks, it means that the mode that corresponds to this frequency will be very, very weakly damped. So now we can put some numbers on all this by defining a damping rate. The smaller is the damping rate, the smaller is the damping. And I have plotted 4 flow conditions from Mach 0 to Mach 0.025. And we can recall, but this time with number, what I just showed you on the last slide. At low frequency, small flow will cause diminution of damping, but when I continue increasing the flow, the damping will increase and will become much greater than without flow. But this will move with frequency, because actually the frequency I'm amplifying with the sound flow interaction are moving also with the flow velocity, until you will reach a zero damping rate for the Mach 0.025. And you can also plot the quality factor to associate it to each of the cavity modes. And what you will see is that at the special Mach number 0.025, I've got a quality factor which is very high, so up than 50 times bigger than without flow. So this really shows that I have really, really, really low damping, and that I could send some informations on very, very long distance if it was not cavity. So I just try to show this by sending a pulse inside my cavity. So without flow, you have all this, you just see, like you send a pulse, so you see the resonances, the modes. So these are 2 spectrograms, and it just lasts 0.01 second. So it's the pulse is just making 1 or 2, or let's say 10 way back and forth. But if you add the 0.025 Mach number flow, you see that actually the cavity plus gain modulus is working as a filter, and you have this frequency that corresponds to the zero damping mode that will last very, very long time, actually more than 2 seconds. And so it's like if the pulse at this frequency is making much more way back and forth, or if it was not cavity but a very long tube, I could send acoustic information on very longer distances than without flow, which can be a way to take advantages for one time of the flow for the acoustics. I will just go back on the damping rate now, but putting ourselves in another, let's say, space. So now each color is corresponding to 1 duct mode, and I'm plotting its damping rate as a function of the Mach number. And actually, so if I am a low frequency mode, I will have with flow, with the low Mach number, a decrease of my damping. But after, as the gain modulus is going towards higher frequency, my damping will be much more higher. Whereas if I'm, for example, the 848 mode, I will have to wait quite a long time in terms of Mach number before to feel any effect of the flow, and to have this decrease until I reach the damping rate 0. We can also plot the same numbers as a function of the Stroll number, so frequency times cavity length divided by flow velocity, and you see that everything is going on one and unique curve, which indicate that the relation between all our duct parameters can be expressed as a function of a unique non-dimensional number. So it's quite classic. Actually, it's really the number that works well with the whistling problems in aeroacoustics, but it's also nice result that it works for this cavity mode experiment. And so last question is what happens for Mach numbers greater than 0.025? What happens is that strong whistling can be heard in the experimental room. So now I'm not sending, so yeah, for all the stuff before, the frequency analysis, I was sending a sweep sinus just to send some acoustic contribution to my system. But now I'm just looking at the background noise provided by the flow, okay? And so and I'm plotting the energy, so power spectral density as a function of frequency. And if I'm below 0.025, so let's say 0.023, I can see that the energy is shared by quite the same level at all frequencies. With on the modes, you have a bit more energy, but there's not a big difference between the mode energy and the rest. When there's some whistling in the room, you have like 4 or until 5 order of magnitudes of difference between the amplitude of the peak, the whistling energy, and the other frequency. And what is interesting is to look at the 0.027, so just after the onset of whistling, and I see that the peak is around 840 Hertz, which was just the frequency I was looking at before. So actually, when I was increasing the flow velocity after 0.025, the gain at this frequency continued to grow. And so my system has too much energy to become unstable, and you have nonlinear saturation process, and so whistling. And so we can link what was happening in the linear regime to what is happening in the nonlinear one. The conclusion is that what we have understood of the physics of corrugated tubes for propagating wave is also working on cavity modes. So one perspective could be to have quantitative number now to tell if we are in the linear or in the nonlinear regime, because for now I'm just capable to tell you, okay, here I was hearing nothing in my room, and after it was whistling, but actually it's not very quantitative. So we are working on quantities and experiments to prove that. And also I think we have maybe some more parallels to make between this experiment, and so let's say aeroacoustic lasers and the classical physics laser, so in both directions. I will be very, very happy to discuss with you about all of these things. Thanks a lot.